So thanks so much for the nice introduction and also for the invitation to speak. It's a real pleasure. And I guess I was just thinking this morning that I've been working on some version of this project on and off since 2004. So that's a long time. And when I came to Boulder 6 years ago, the idea was to get going right away and really go to the mid-infrared. And it's actually only recently that we've received, or we're going to be receiving funding to really go there. So it's actually a very exciting time, and I'd like to share my excitement with you this morning. So before I get going, I just want to say this is a picture actually that my student Molly took, and it's actually of some waveguides that we've made and a fiber that's coupling in, and then this is a scanning electron micrograph of our waveguides that are 2 microns by 90 nanometers tall. So here's an outline of my talk. So first I'd just like to give you an introduction to who we are in the ECE department, who do optics and nanostructures and bio, and then I'll go ahead and tell you about why you would actually want to go to the mid-infrared region, because it's actually quite challenging to do a project in this region. So you better have some good reasons for wanting to endure the pain. And then I'm going to tell you about nonlinear optics. So when we started this project a couple years ago through NSF, the dream was basically to be able to do nonlinear optics with laser pointer in the mid-infrared. And so in order to do that, you need a mid-IR material. You need it needs to be nonlinear, and then you want to play as many tricks as you can to increase the nonlinearity, so you have to use very little power. And our solution has been to use a chalcogenide platform that I'll be talking about, and then finally I'll conclude. And if there's extra time, I'll tell you about some of the other things that, some of the other exciting things that we're doing in my group. So first, I guess I'd just like to introduce you to the Bio-Optics Nano Group, or BON group, which is, it's actually the largest faculty group in the ECE department. So we work on 4 main areas. One of them is optoelectronic materials and devices. We work on quantum and ultrafast laser systems, and then electronic photonic integrated microsystems, and computational imaging, microscopy, and lithography. So the group is quite diverse, and I think these 4 areas really capture the strengths. So here's a picture of the faculty. There are actually 12 faculty working on various aspects of the research that I've outlined. And so I guess I'd like to tell you a little bit about my group. So my group essentially has applied physics. So my home is in electrical engineering, but I actually have a courtesy appointment in physics and also in material science. And so we have a lot of projects going on. This is actually our waveguide characterization setup and one of the ultrafast fiber lasers. We also love doing outreach to get younger students interested. So my research spans things like looking at more efficient ways to get pulses out of diode lasers. This is a quite important area. Examining mid-infrared lasers in the chemical fingerprint region, optofluidics for adaptive devices, spectroscopy, beams with a twist. This is orbital angular momentum. And finally, what I'm going to be talking about today, which is nonlinear optics with integrated devices for the mid-infrared. So there's a large range of things that I'm interested in, and I guess I've been fortunate that we actually have activities in most of the things that are listed on the slide. So I guess let me tell you a little bit about why we want to go to the mid-infrared. So this is actually a picture of a fumarole in Italy. And so before a volcano erupts, it actually emits, it starts emitting gases. And so there's actually a monitor in here that's actually monitoring at 1.5 microns. There's a laser that's monitoring what's coming out. And so if you can shift this to the mid-infrared, the absorption will be the laser will be much stronger, and so you'll be able to have a much more sensitive early warning system to get people out of the way of a natural disaster. And to illustrate that, this is actually an absorption coefficient of acetylene, which is from the HITRAN database. It's basically the accepted database where you go to look for absorption lines. And so this is the near infrared, and this is the mid infrared. And so you can see that you basically really win as far as the absorption of these molecules. As you think about these, if you think about these molecules, you can think about them like a ball and spring model, and so a lot of them have resonances between 3 to 5 microns. And so when you look in the near IR, you're looking at an overtone of that, and so that overtone is correspondingly weaker. So the other thing I would say is this is basically looking at all the different all kinds of different molecules over a wavelength range of 1 to 7 microns, and so you can see there's all kinds of spectral signatures in the mid-infrared. And I know for sure that I mean, there are a lot of applications, and I guess to validate this point, last year there was actually a big DARPA program that started based on this. So I guess I just wanted to tell you a little bit more about some of the various things that impact your life as to why you would care about having mid-IR sensors. So for anti-terror efforts, if you go to the airport and you get scanned, pollutants, combustion monitoring, and then industry, like if you're processing a chip and you want to know how far you've etched, it'd be nice if you didn't have to take the chip out and actually measure it, if you could just measure the byproducts. So this is actually looking at detecting carbon dioxide at 15 microns. And I guess I should also say that the mid-infrared region, the definition of it is a little bit squishy as to whether is it 3 to 12 microns, is it 3 to 5 microns, is it 8 to 10 microns. For the purposes of my talk, I'm going to be focusing on 3 to 5 microns, but as far as the motivation, it covers the wider range. So it also has applications in agriculture, medicine, and finally, things like free space communications. So there's actually a transmission window in the atmosphere between 3 to 5 microns, and it can also be used for countermeasures. So there are many reasons. There are many reasons to go there. It doesn't necessarily mean that it's easy. And so I just have a few, actually have a few examples of looking at various processes that have been implemented in the mid-infrared. So this is exactly what I was telling you, that you have this, you're measuring, you're etching something, and then you're measuring the HCl absorption versus wavelength. And if you think about, probably all of you have a computer, and so as the semiconductor industry makes things smaller and smaller, they need more and more control over these processes. The current transistor dimensions are about 22 nanometers, and there's actually a whole bunch of problems with the fabrication at that kind of at that sort of dimension. So I guess I'd also just like to say that that this can be used for explosive detection. So basically in explosives, they look for nitrogen oxide. So actually, I went to the airport about a month ago, and to my horror, I tested positive for explosives. But the thing is, the airport machine, they're looking for a few key compounds, and those compounds are found in other things, such as shoe polish or like fertilizer, et cetera. So the point is that if you look, this is a plot of the transmission versus wave number. The absorption, the transmission goes down as you get to the mid-infrared, and so you can make a more sensitive system. What you'd really like to do is you'd like to have what's called a standoff system, where you have a laser and then you have, your object that you're trying to interrogate. So you're not making it obvious to whoever you're wondering about. So I guess, gosh, it looks like something really got messed up with this talk. I think it might be the resolution, but I guess if we change the resolution back, it will really mess everything up. So all my stuff has moved. All my stuff has moved around now.
The sides on the bottom are a little bit cut off, so I guess it's a trade-off between which part of the talk you want cut off.
Yeah. So does anyone know how to change the resolution? Because I think. Okay. So let me just see. Yeah, I guess I should have been more careful. Let me just. But I think now the resolution has changed, so everything on the talk has moved around. So anyhow, let me just try and keep going, I guess. I'll just try and. Yeah, I didn't realize this was going to happen. Let's see. I'd just like you to be able to see the words. That's all I'm trying to do. So the point is that essentially, if you look at the transmission of fused silica, you can see that there's this short wavelength cutoff, and then there's also a long wavelength cutoff. So basically, what I wanted to tell you about is why it's hard to operate in the mid-infrared. Why is it hard to get sources, and why is it difficult to get materials? So the point is that you've got this short wavelength cutoff that is due to electronic transitions, but on the other side, you may or may not know, but this rolls over due to phonons. So this is basically the absorption of the lattice vibrations. And so if you think about the materials as like a ball and spring model, as you make the atoms like heavier and heavier, then that resonance frequency for the phonons goes further and further out into the mid-infrared. So the point is that fused silica is only good to about 3,000 nanometers, and then it sort of stops. And so this is really problematic in the sense that if you want to use optical fiber or you want to use any kind of silicon devices, you now have trouble. So I guess the other thing that's kind of covered up here is that additionally, in order to get lasers going, you need to have a material that has optical gain. And so if you look at the rare earth atoms, you will see that there's only just a few transitions between 3 to 4 microns. And so what does that mean? That essentially means that there are no fiber lasers and there are no solid state lasers at these mid-infrared lasers, mid-infrared wavelengths. So, and then the final straw is that if you look at semiconductor lasers, which you can think of as being some of the most successful lasers because they're really, really small and they're also really cheap and they're electrically pumped, unlike fiber and solid state lasers, they suffer from this loss called Auger recombination, which is where you have an electron and a hole that recombine, and now that energy goes into knocking another electron or a hole further into the band. And so this effect gets worse and worse. So at 1.5 microns, it's around 50% of the threshold of a conventional laser. And so you can imagine by the time you get to 3 microns, you just can't do anything. And so what does this mean? This also means that there are no conventional semiconductor lasers at mid-infrared wavelengths. So yeah, I think some of the talk got messed up because of the resolution change. So, but I'll just keep going. So what is nonlinear optics? Nonlinear optics actually was first observed. Theodore Maiman first demonstrated the ruby laser in 1960. You may or may not know, but he's actually a graduate from CU in engineering physics. And then 1 year later, there was actually an experiment done in nonlinear optics. So if you think about it, it's the study of interaction of very intense light with matter. And you can also think about the medium has this nonlinear response to the applied field. And so you can describe it with nonlinear polarization. So essentially that you have this chi3, or you have chi1, chi2, and chi3, and then this continues. And so, so for the rest of the talk, I'm actually going to be focusing on chi3 processes. These are the first ones that you see in amorphous materials, and chalcogenides, or at least the type of chalcogenides that I'll be talking about, are amorphous. So chi3 nonlinearities lead to a lot of things that you may have heard of. One of them is saturable absorption. So this effect that essentially, as you hit a sample that absorbs with more and more intense light, eventually all the states become full and it's bleached. And the second thing that this is responsible for is the nonlinear refractive index. So this is essentially that if you eliminate a sample with intense light, instead of just having a baseline refractive index of n0, it actually changes with this product of n2, which is the nonlinear refractive index, and I, which is the intensity or the square of the electric field. And so this is responsible for spectral broadening, switching, and then there's also Fourier mixing. So in order to get any of these processes, you need momentum and energy conservation. So I just wanted to talk a little bit more about self-phase modulation and forward mixing because it's kind of the direction that we want to go with the devices for the mid-infrared. So essentially, you get a phase shift experienced by the optical field when it propagates. And so what happens is this generates new colors, as you can see in this plot. This is basically sending light through 1 centimeter of fiber and then increasing the optical power, and you can see you get more and more broadening. And then forward mixing is basically where you illuminate with 1 or 2 colors, and then you get 2 new colors out. And so why would you want to do this? This is actually a plot from a science paper from just a few years ago, showing that if you come in with to a device with just a single wavelength, you can broaden all the way. You can almost get an octave of broadening, and this is due to forward mixing. So the other thing you need for forward mixing is you need what's called phase matching or momentum conservation. So you basically need all the k vectors to make sure the difference between the k vectors to add up to 0. And then I couldn't resist making a slide about this last night. So many of you may have seen this. This is actually the paper for the first nonlinear optics experiment. And it's done in 1961 with Maimann's ruby laser. And so you had second harmonic generation. So this is the fundamental. And there should have been a very small dot here, but the editor thought it was a speck of dust. So he removed it. And they never published it erratum, and so it's considered to be a joke in the nonlinear optics community. So you know, it's I guess it's easy. It's easy sometimes when working in this field to feel a bit depressed, like, oh, you know, the laser came out, and then all these people discovered all this nonlinear optics like in 1960. So what is there to do in 2015? It turns out there's still a lot. And so I guess nonlinear optics. If I think about the progression from 1960 to now, it's really like the power that's needed in order to get these effects has just gone down, and it's gone down for a number of reasons. So first, you need a pretty powerful laser, and then along came fibers, and then these periodically pulled crystals, which are essentially engineered crystals that have a high nonlinearity, and then there are the microstructure fibers that were responsible for the Nobel Prize in optical clockwork, and finally there are integrated optical devices. So each of these is like pulling the threshold for nonlinear optics down further and further. And so this is actually a result from my grad school days. So I'm sure you can relate. This is actually a microstructure fiber that's sitting on top of a Kleenex box, and so you're generating third harmonic of 1550 here. So if you think about what you want for a nonlinear mid-infrared material, you want something that's going to give you this low threshold that I talked about, and you also want something that will be able to generate this broad spectra. So that means you need something that's highly nonlinear, and you also need something that's quite transparent. So if you look here, this is actually a plot from Michal Libson's group at Cornell. So this is actually looking at basically spectral or Fourier mixing in a silicon microresonator, and so you can see that she's been able to cover from 2 microns to 3 microns. So we need to select a highly nonlinear transparent material, study the nonlinearities and the losses of this material as a function of wavelength, so we understand what's going to happen, and then also choose a waveguide geometry so we can further reduce the threshold. And as far as what can you use this for, as I mentioned, there's this big DARPA program that came out on sensing, but it's also really important for communications, also medicine and imaging. So even though there's a lot of absorption, there are reasons why you might want to do your imaging there. So anyhow, so this one looks like it got a bit messed up, but I'll just keep going. So essentially, you can argue till the cows come home about what a chalcogenide is. Chalcogenides can either be crystalline or amorphous, but as I said, I'm going to be talking about amorphous ones. So if we think about amorphous semiconductors, then they contain, the definition is they contain sulfur, selenium, or tellurium covalently bonded to one other element. So from this area of the periodic table. And so the advantages are that, as I was mentioning, the chalcogenides have very heavy atoms, and so that means they have long wavelengths transparency, they have a large nonlinear refractive index, and they also have what's called an excellent figure of merit. So the figure of merit is basically the ratio of the nonlinearity to the 2-photon absorption. So the 2-photon absorption will basically steal away your steal your field from the nonlinearity. So chalcogenides are actually used widely in rewritable CDs and DVDs, and then they're also used for, this is a picture of commercial chalcogenide optical fiber, and then this is a picture, I was just thinking about this was amazing. So this is actually a picture of a layered chalcogenide fiber from Yoel Fink's group at MIT. So what he did is he actually had a hollow core, and then it's got layers of polymer and chalcogenide and polymer and chalcogenide. And so there's such a large refractive index difference, it acts like a perfect mirror. And so the story of this is that he actually published the theory for this, and it made a big impact, and people said, oh, you can never do it. You'll never be able to make it. And then he was able to make it and started a company. And so this was quite some time ago in about 2000. And the company's still going. So I think, I guess the bottom line here is that I think there's actually a lot of promise. So I guess I just wanted to maybe quantify a bit more what I talked about more generally. So if we think about mid-infrared devices, we talked about the long wavelength transparency, the high nonlinearity, low nonlinear loss. And then, it's really nice. You never get anything for free. So when you go to these materials that have longer wavelength transparency, it means that their mechanical strength might not be so good, or their melting temperature might be really low. And then this makes it really hard to do any kind of processing. And so, we're looking for something that has a high glass transition temperature, and also is mechanically robust. So. And I guess I'd also just like to touch on the fact that chalcogenides have kind of a bad name because of photosensitivity and low damage threshold. And this is essentially because people are operating them too close to the band gap. So I mentioned to you that we're looking at, or the focus of my studies have been on amorphous materials. And so amorphous materials don't have a sharp band gap. There's actually a tail. And so you still get some linear absorption even when you're not exactly when you think you're below the band edge. And so this can lead to photosensitivity and also photodarkening. And so if you go to the mid-infrared, most chalcogenides actually have the band gap in the visible, and so you will be really far away from those effects. And then if the goal is to basically operate at low power, then you're essentially operating in the corner of the graph of the trade-off space that is right for these materials. So at the bottom, what I have is this is a plot basically comparing the nonlinearity, two-photon absorption, figure of merit, transparency, and glass transition temperature for a few different materials. And so most people are familiar with fused silica since it's in optical fibers. So you can see silicon, and this is all for 1.5 microns. And so, and the reason for this is because at 3 microns, it's still a region that's being explored, so we still don't have all the values. So if you look at silicon, it's considerably better. If we look at arsenic triselenide, it's also pretty good. And then a material that I'll be focusing on later in the talk is this germanium antimony selenide, and you can see that it's considerably better than fused silica. And if you look at the two-photon absorption, you can see that silicon's got quite a bit compared with this material. And so if you look at the figure of merit, not surprisingly, the silicon is not so good. But the chalcogenide is quite a bit better. So if you look at the transparency of silica is actually expected to be 0.2 to 2.2 microns. Silicon's 1 to 7 microns. This arsenic triselenide is 1 to 12 microns, and the germanium antimony selenide is 1 to 14 microns. And so you can see also that if you move away from these arsenic selenide compounds, you can do better with the glass transition temperature, although still not as good as fused silica. So that's kind of the decision process that goes into this. And yes, there are other materials to look at other than chalcogenides. I mean, chalcogenides are nice in the sense that since they're not crystalline, you can do things like thermally evaporating them or using pulse laser deposition, and then that gives you actually a lot of freedom as to what kind of substrate you choose. So I started putting together this slide last night. And I was really just blown away with the amount of work that's being done. There was a lot of work that was done, in 2000, and then people kind of went away from it. But more recently, there's been all this fiber work. There's been a lot of waveguide work. This is actually a chalcogenide ring-based sensor. This is a ring that was demonstrated with really low loss. Here, this is actually a fiber taper, a nanotaper, and this is an example of using a chalcogenide device in a communication system. So there's really a lot of activity in the field as the fabrication processing has got better and people have kind of understood sort of how to operate these materials in a way that's beneficial. So one of the things about these glasses that is hard is that they really have to be mixed up properly. Otherwise, you don't get repeatable results. And so this is actually a picture of a rocking furnace. It's actually from OmniGuide, which is the company that you'll think started. And so essentially, they mix everything up for like 12 hours in this special furnace. And then they also go through a distillation step to try and get rid of any kind of impurities, such as oxygen, and then cut and polish them into thick windows. So I think there are a number of really reliable suppliers now, so this is not becoming a problem, but you have to be careful to make sure that your stoichiometry and your material is mixed up properly. Because I guess even though these chalcogenides are amorphous, they actually have some long range order associated with them, and so you don't want to destroy that. So, I mean, the first thing to do when you're considering a material for nonlinear optics is to try and characterize the nonlinearity. And so, I mean, you can look at the nonlinear absorption because that's just going to give you an intensity. Drop. But when you think about the nonlinearity actually gives you a phase shift. And so traditionally, optical-based phase shifts are much harder to measure. So this is actually a really elegant method using just a single beam, no interference, where essentially we have our sample and it's placed at the waist of this focus beam, and then it's scanned around in minus and plus Z. And so essentially what happens is, like, when you're at the focus, the beam is most intense here, and so it causes the sample to act like a lens. And so if you have an aperture here, then you'll essentially see that there's less light that goes through. And then as you translate around to places where the beam is less intense, then the sample won't act so much like a lens. So essentially you can get these traces out. This is a case with the aperture, and this is a case without the aperture, and then you can fit them and extract the nonlinearity and the two-photon absorption. So this is actually for a germanium arsenic selenide compound. It's actually sold commercially as Amtir, and as I said, it was actually what started this foray into the nonlinear mid-infrared. So we did closed aperture Z-scan, showed that we could get basically significant enhancement over fused silica, and then also looked at the two-photon absorption, which was a bit difficult to measure. And I guess I just wanted to mention that there is another way that you can look. You can actually look at both the nonlinear refractive index and also the two-photon absorption, and that is to do what's called pump probe. So essentially, you have a strong pulse that comes in, and then it's split into a pump path and then a probe path. And the idea here is that the pump is really intense, and the probe, and so it will perturb the sample, and then the probe will come in at like a varying time delay, and it's much smaller, and it will basically just watch the sample relax back down. It won't actually perturb the sample. And so this is just a case of single wavelength cross-polarized pump probe, and so essentially we focus this onto a sample with a variable time delay between the pump and the probe, and you can get a trace like this. And from this trace, you can also extract the two-photon absorption. And if you do some more work, you can also set this up so that you can extract phase shifts. The issue with this geometry is now you don't have a single beam that's focusing into the sample. Instead, you've got two beams. So you've got to overlap them, and you've got to get them to behave the same way. And so it can be a little bit more tricky to figure out what's going on if your alignment is not perfect. Because, for example, like you could know exactly what's going on with your pump beam, but if your probe beam is only like 10% over your pump beam, then you're not going to get a result that you can hang your hat on. So anyhow, I just wanted to show you a few results from this initial study. We basically looked at a number of germanium arsenic selenide compounds and just changed the germanium content, and then I guess also the arsenic and the selenide content just slightly. So it changed the band gap just a little bit, not even 100 nanometers. But you can see that it had a huge effect on the nonlinear refractive index, basically going from 200 to 900 times that of Fusilica. Not much effect on the 2-photon absorption, not much effect on the glass transition temperature, and then also big effect on the figure of merit. So the point is, these glasses, I made this comment that earlier that you really have to make sure your glasses are mixed up and that they're like properly put together. From this, you can see how important that is. So we did have some theories about what was going on. So basically, we've done a study where we're changing the band gap as well, but we're keeping our laser fixed. And so as you get to half the electronic band gap, you essentially see a maximum just below the half gap. And then there's also a lone electron pair theory with increasing germanium content that's being used for other chalcogenide glasses. And there's also the potential for decreasing stoichiometry and related defect states. So there are a number of things to think about with this study. But anyhow, I just wanted to give you just a brief look at the stuff that got me interested. The actual idea with this project was that we were going to measure these glasses and then make them into nonlinear fiber. And then when they tried to make it into nonlinear fiber, the materials looked fine at the bulk, and then they pulled them down, and there was all kinds of absorption. So we weren't able to get very far. I guess it's being sorted out now. So basically, there's a change in the material as it got pulled down to these really tiny lengths. But anyhow, so since I've been at CU, we've been looking at a different material. We've been looking at germanium antimony selenide, and the reason for this is that we have a thermal evaporator, but we didn't want to deal with evaporating arsenic because, as you know, arsenic is very toxic. So that was kind of the criteria, that we wanted something that was arsenic-free, and we wanted something that will evaporate with good stoichiometry. We want high glass transition temperature, so we have as many options for processing as possible. And then for us, it's nice that it's commercially available. And if we look at the linear loss, it's actually quite low. So this is looking at the index of refraction and then also the dispersion, showing that there's a 0 when you get to the mid-IR, which is probably quite important for the making nonlinear mid-infrared devices. So I guess what we're learning as we move forward with these projects is that it's actually very important to characterize not only the nonlinearity and the nonlinear loss, but also the linear loss. And so this is actually a setup to characterize the linear absorption. So essentially, there's this special angle called Brewster's angle where you would expect you would get no reflection. But if you now add absorption, the Brewster's angle changes slightly. And so if you set up your sample on a stage and then you measure the transmitted and then also the reflected power as a function of angle, you can figure out what's going on. And so with this, we were able to measure both the absorption at 1 micron and also 1.5 micron, as well as put like an order of magnitude estimate at 3 microns as to what we'd expect. So essentially, we just have a laser that, or we had an alignment laser that came in because we couldn't see anything, but then we have a 1550 laser and just half-wave plate, polarizing beam splitter, the sample, and then a few things to measure both the reflected and then also the transmitted power. So it's a fairly simple technique, but I guess when you're trying to measure small absorptions, you can't just put a photodetector before the sample and after the sample. You have to go to something much more sophisticated. So this is so the next thing that we wanted to do was look at the nonlinear properties. So this is a diagram of the setup. So we have a source, and then some wave plates, and then the sample on a translation stage, and then our aperture, a lens, and then a detector. And we have both short and long pulses and pulsed lasers in our lab. It turns out the long pulse laser is not so good because it excites free carriers. But we also, and so this one is at 1 micron. We also have a similar one at 1.5 microns that we can use. So again, this is the same thing. We did Z-scan measure the nonlinearities, we used 200 femtosecond pulses at 1030 nanometers. And so this is actually a very interesting plot, and one I think that we struggled with quite a bit. So this is looking at the 2-photon absorption as a function of rep rates. So this is kilohertz, and then this is megahertz rep rate. And so you can see there's actually a big difference. And in the case of the megahertz rep rate, there's actually some significant variation. And then if we look at the nonlinear refractive index, we see sort of a similar thing, that the kilohertz data is basically constant, but the megahertz data is changing as a function of intensity. So the question is, what's going on? And what's going on is that we're actually getting what's called photodarkening. So there's actually some basically, if your pulse comes in and then the sample can't relax quickly enough, then you can essentially change the bond structure and change the way it's responding. So the values that are really relevant for us are the ones that are measured at the kilohertz. So this 1030 nanometers is pretty close to the band edge, so that's why we have quite a large 2-photon absorption. And then here's our nonlinearity that we've measured. So just to summarize where I am so far. So this is a summary of our measurements at 1 micron, and then we've recently moved to 1.5 microns. These are actually results from Gotti Lenz's paper from 2000, and we're currently moving this direction. So now I'd actually like to talk about making waveguides, because this is something that can basically increase the nonlinearity. So as I mentioned, there are a number of options for amorphous materials for deposition. And so kind of the 3 main ones for chalcogenide are pulse laser deposition, RF sputtering, and thermal evaporation. So the thermal evaporation is really simple. You actually don't need a pretty inexpensive piece of equipment to do this, and it can yield really high quality films with a simple technique. And so our fabrication process is based on what's called liftoff. So we start with a fused silica and a silicon substrate. We put resist on top, we evaporate, and then we lift off. So this is nice because then we don't need to use any kind of etching. So it's actually, as I mentioned, it's very important to understand the stoichiometry of the films that you have. So if we look at the thin film relative to the bulk, you can see that we're very, very close. We're within 4%. And then if we look at the band gaps trends are consistent with literature, and they're a little bit different, but very, very close. So this is the scanning electron micrograph I showed you at the beginning of the talk. So here, this is actually really wide. This is about 2 microns wide by 90 nanometers in height. And it's just a strip waveguide evaporated on silicon dioxide. This is actually a picture of the simulated optical mode from the mode solver. And if you ask why we chose to go with such an asymmetric waveguide, the reason is because this is something that can be easily fabricated in our clean room with photolithography. So after making the waveguides, the next thing to do, or in parallel, is to essentially put together a setup to characterize it. Say, okay, fine. Many people have done this. So actually, not so easy, but we have one together that's working quite well. So we have a ytterbium or erbium doped fiber, and then this is going through some polarization control through a nonlinear fiber, and then it's focused down to a waveguide. Actually, it's not nonlinear. It's just a high numerical aperture fiber. We have the waveguide, and then we have a collection on the other side. So we use piezo stages for control, and the really exciting thing from these measurements was that when we looked at the 2-photon absorption coefficient of our thin films, it's within a factor of 2 over our bulk material. So that's really promising for moving forward. So we also looked at the so this is a few more details about the 2-photon absorption. So essentially, you can measure the transmission versus incident intensity to determine this. And we use 7 picosecond pulses. You can apply this equation and then fit to this is the reciprocal transmission versus incident peak intensity. So this might be useful for optical limiting near 1 micron. And as we go further from the band gap, this will become much less of a problem. So it's also, as I mentioned a few slides ago, it's very important to be able to characterize both the linear and the nonlinear loss, because if you both of these will steal away from the power that you have available for the nonlinear optics. So if you think about the linear loss, essentially you get scattering from the top surface and the sides, and you can essentially look at the material absorption by just doing an integration of the absorption coefficient as a function of position scaled by the field. So if you think about, so here's a schematic of our waveguide. This is the high index waveguide on top of the low index cladding. And then here you can characterize the surface with the autocorrelation function using the RMS surface roughness, and then compute the radiation in the far field. So it turns out actually simulating this loss is not an easy thing, and essentially we're lucky in the case of the strip waveguides in that we have the field will see much more of the surface, and so we can estimate the loss by because it's dominated by the surface roughness. But once we go to more symmetric structures, then we have to be a bit more careful. We have to be a bit more careful with the theory. So this is actually the general theory for the loss from a waveguide from Payne and Lacey. And I guess I'd just like to mention that this depends on the square of the core refractive index minus the cladding index squared. And so basically there's this trade-off. If you have high index contrast structures, then any kind of scattering that you have at this interface will be amplified and turn into loss. When you make the index contrast lower, then the structure has to get bigger, and so it's harder to control the dispersion and the nonlinearity. So there's definitely a trade-off there. And if you have an exponential or autocorrelation, then things simplify, and so this basically goes as the thickness to the fourth power. And I guess this isn't. I don't have a slide about this, but it's actually very interesting. We've done the analysis that shows that if you scale, if you look at how the loss scales with wavelength, it scales approximately, we think, with 1 over lambda cubed. So basically, as you go to longer wavelengths, you will be able to achieve lower loss structures if your loss is dominated by like interface roughness. So actually measuring the loss, there are a number of different techniques for doing this. So one is basically that you have different waveguides of different lengths, and you just couple into each of them. The problem here is that if your coupling efficiency is not the same, then it can be very hard to back things out. You can use the Fabry-Perot transmission method, which is essentially you launch light in, and then you look at the multiple reflections coming out. But if your facets aren't perfect, that can be a problem. So we've actually been using the scattered light method because it doesn't depend on, it's insensitive to coupling efficiency. So essentially you launch light in, we have this camera, and then we plot this exponential decay of the intensity as a function of wavelength. So I guess the trade-off here is that if you have really low loss waveguides, it may be difficult to see what's going on. So this is a summary of the designs that we put together. So at 1030, we had this 2.2 micron width waveguide by 45 nanometers high, and at 1530 nanometers, we used a 2 micron waveguide by 90 nanometers high. And so we looked at the roughness of both the top and the sidewalls. And so on the top, we have 0.8 nanometer RMS roughness, and the sidewalls we have 11 nanometers. But as I said, we're really dominated by the surface roughness in both of these cases. So this is a setup of the loss measurement. It's very similar to what I showed you before. So we have these imaging optics that are mounted on top of the waveguide, and essentially you can do this with low power. That's what you want to do, and then just measure the intensity versus position. Yes. Okay. So these are some results from the loss measurements. So this is basically the power plotted as a distance along the waveguide. And so the blue is the 1030 nanometer data, and the purple is the 50 nanometer data. And so what you can see is that our loss at 1 micron is quite high, 12 dB per centimeter. But when we went to 1530, just with one try, we were able to get down to 4 dB per centimeter. And it's very clear that if we look at the theory, that this is basically coming from the surface roughness. I guess the good news is that the measurements agree with theoretical predictions. It's comparable to the results in the literature, and we understand exactly where the loss is coming from. And so the next thing to do now is to go to a kind of a more symmetric waveguide for a number of reasons, but the main reason is to try and reduce the loss and increase the nonlinearity and control the dispersion. So I guess I showed you that we've, so I guess we haven't moved all the way to the mid-infrared yet, but we're in the process of building a laser, and we hope to be there by the fall. So right now we've characterized the bulk and these thermally evaporated waveguides. We've shown the nonlinearity at least at 1 micron is 100 times that of fused silica. The figure of merits should improve even further as we go further from the 2-photon absorption, and this makes it a promising arsenic-free platform. So we're going to continue our characterization at 1550 in the mid-infrared, put together a 3 micron optical parametric oscillator, and then also look at frequency cone generation in the mid-infrared. So I'd like to acknowledge my collaborators in this work. A lot of the data that you saw here is from Molly, and also Sungmo An, who's a postdoc who's working on this. This work was done in collaboration with Professor Juan Park, Ms. Popovich, Peter Rikic, and Timon Barwitz, and some of the stuff that I showed you earlier. This is from my PhD, so from MIT. And then this is a picture of my group, and I've got 3 grad students and undergraduate, and I'm definitely looking to hire some more people, including for this project in the fall. So thanks so much. So we're actually going to start with a 1 micron laser. We're going to amplify it up, and then we're actually going to use piplin, periodically pulled lithium niobate, because it's standardly available, and I won't have any problem as to getting out as much power as I want. And then it's also very tunable.
Yeah. Do you think anybody will ever successfully dope chalcogenide and just laze straight from it as a fiber laser?
I guess I'm a little bit skeptical of that, and then the reason I'm skeptical is because, as I mentioned, as you go to these materials that have lower phonon energy, they also have lower thermal conductivity, and so when you think about putting a laser together, you're talking about high powers. So I guess what I would say is it would have to be heat sunk really, really well. So I guess I don't think it's out of the question, but I think there are probably a lot of barriers that need to be overcome. And I guess the other question is, what are you going to dope it with? Because erbium and holmium and thulium, they have these few transitions between 3 to 4 microns, and then there's absolutely nothing. Mm-hmm. So, and actually we did look at buying a QCL for the work, but the QCLs are unbelievably expensive for for very little power that comes out. So I think there's really a need to, even if we think about these frequency converted sources to move forward.
How worried you are about the dispersion in these. It looked fairly significant, especially as you go further away. Think you'll be able to effectively compensate, or are you going to be really fundamentally limited on the amount of non-linear material you can use?
So with the dispersion, what I showed you is a plot of the material dispersion, and so if we make waveguides, there will also be a dispersion effect from the geometry. So we can use the geometry to compensate some of that. So the smaller the waveguides, the more contribution from the geometrical dispersion we'll get. There's going to be some limit as to what we can do. But I think there's a large range over which it's fairly flat and hanging close to 0. So I think that's a good place to operate. The other thing I'd say is that we've been doing some looking into the frequency comb generation, and I guess the most important thing is the dispersion at the pump wavelength, like not that it's flat like everywhere else. And so in that sense, that's good news. Yes.
So we sort of discussed this in the class I took with you, but how does the nonlinear refractive index affect the guiding mode and all of the waveguides you discussed? Like, is there some sort of balancing between, like the nonlinear part, and then if the mode changes size but the waveguide doesn't, how does that affect things in your setup?
So I think our waveguides are small enough, and we don't have like big changes in aperture or whatnot that I don't think we're having any problems with. I think what you're asking about is self-focusing.
Yeah.
So what people want is they want to basically stay below that threshold. Like that's that's like kind of one of the limits in optical fibers. And so I think we should try to stay below that threshold, or try to see if we can mitigate it. So. But it can be a big problem, like as you go to high powers, and not even just pulsed, but also CW if you scale up the power.
I think we'll have to
Okay.
have a question.
Thanks.